So in today's video, we'll look at the derivative as a function. Our main focus before this has been the derivative at a single value, a. Now we're going to think of it as a function that can be represented at all values of x. So the difference here is we have x's instead of a's. So our definition of the derivative for our h way, we've got limit as h approaches 0 of f of x plus h minus f of x all over h. Now, if you were to do it the a way, the difference would be at the end, you would have to replace your a with an x. Okay, you could still do that. I prefer the h way, but if you would like to do the other way, just make sure at the very end you replace your a with an x to make sure it is a function of x. Now, some alternative notations other than f prime of x. We'll see y prime. We will see dy over dx. That is Leibniz notation. And then there's some other notations there. We will not see those as frequently. Okay, those first three listed there are the most common three that we will see. And so you want to be able to recognize if you see them in a problem and it says to find that you're really just finding the derivative. So what we're going to do is we're going to look at this graph of f and see if we can roughly piece together what the graph of f prime should look like. Well, keep in mind, our derivative is really the slope of our tangent line. So our y values in our derivative should be the same values as the slopes in the original. So a good thing to do to start is to plot where these slopes are 0. So we have a slope of 0 here, so we'll plot a y value of 0. We've got a slope of 0 here, so we'll plot another y value of 0. We've got another slope of 0 there, so we'll plot another y value of 0. So that's always a good start. And what we'll do is just at certain points, we'll see what number roughly represents the slope, and we'll plot that y value. So for example, kind of a little bit before the y-axis there, the slope looked like it's maybe -2. So I'm going to plot a y value down here, roughly where -2 might be located. And around the x value of 1 there, our slope looked like it's about +1 or so. So I'll put a y value up at +1. Now, in between our next two zeros, the slope probably gets as steep as it probably does. So we'll make it, and it's negative, so we'll maybe make a point down here. And then our last section there, after our last turning point, the slope is positive, but it's a pretty small positive number, and then it's gradually increasing. So we'll maybe put like a small positive number here, and then it keeps getting a little bit bigger or so as time goes on, our y values. So if we sketch that in, our derivative graph maybe looks something kind of like that. Okay, and that's how you can piece together what it is. Just kind of look at what the numerical values of the slopes are, and those are the y values in your derivative graph. Okay, and here's a more exact version of that, and what we had was quite close to that. So the blue is our f of x, and the pink there is the f prime, the derivative function. So what we're going to do now, we're going to use our definition of the derivative to find f prime as a function of x. And to do that, remember we have our limit as h approaches 0. We now have f of x plus h minus f of x all over h. So this will be the limit as h approaches 0. We will have x plus h subbed in for x, so we'll have x plus h cubed minus, we'll have x plus h in parentheses again. And now minus f of x. Remember, if f of x is going to have more than one part, make sure you put it in parentheses. So we will have x cubed minus x all over 8. So we'll now have the limit as h approaches 0. I'm going to go off to the side, and we'll multiply out this x plus h 3 times. So multiply it out once, we get x squared plus xh plus xh plus h squared. So that's really x squared plus 2xh plus h squared. And then we'll have to multiply that with another x plus h. Well, when you distribute the x plus x squared h, when you distribute the 2xh, you'll get plus 2x squared h, and then plus 2xh squared. Distribute the h squared, you'll get xh squared plus h cubed. And if we combine our like terms for that, that's going to give us x cubed plus 3x squared h plus 3x h squared plus h cubed. Okay, that's just that first cube that we did out. We've got to distribute the negative, so we'll have minus x minus h. We'll distribute our other negatives, so we'll have minus x cubed plus x. And this will all be over h. Well, our things without h's should add to 0. We've got a positive x cubed and a negative x cubed. We've got a negative x, we've got a positive x. So if we rewrite our limit, again, it's important to carry that limit down each time until you do direct substitution. We will have 3x squared h plus 3xh squared plus h cubed minus h all over h. And we can now divide an h out of everything. We'll have limit as h approaches 0. We'll be left with 3x squared because that h divides out. We'll have plus 3xh because one of the h's divides out, plus h squared. And then this last part is where people make an error. They just won't write anything, but really you're doing negative h divided by h, so that's really negative 1. We are ready to do our direct substitution. If we sub in 0 for all of our h's, we will end up with 3x squared minus 1, and that is what f prime of x equals, our function for the derivative. And what this function represents is if we sub in any x value, it could give us the slope of the tangent line. Okay? And that is very important because you wouldn't want to have to do your definition of a derivative for tons of different a values. Okay? A values are different locations where we might want the derivative. So if we want the derivative at 4 different locations, the actual slope of the tangent line, this can now allow us to quickly find that. And here's a graph of those. And you can just visually inspect that it makes sense. Notice we have a turning point, a horizontal tangent line a little bit to the left of the y-axis, which represents our 0 on the derivative. And then we have another turning point there a little to the right of the y-axis, which is our 0 on the derivative. So our slopes in the original should match the y values in the derivative. We had positive slopes for a while, switching to negative slopes, and then back to positive slopes, which match our y values in our derivative graph. So we're going to look at another example. We'll find our derivative as a function for square root of x. Of square root of x plus h minus square root of x all over h. Because we have square roots, we'll do conjugates. So we'll multiply top and bottom by square root of x plus h plus square root of x. So this will now be the limit as h approaches 0. We will have x plus h. Outside and inside terms wipe out. Then we'll have a minus x h times square root of x plus h plus square root of x. So this will become limit as h approaches 0. We will have h over h times square root of x plus h plus square root of x. The h's wipe out, giving us limit as h approaches 0 of 1 over square root of x plus h plus square root of x. And now this is something we can do with direct substitution. We'll sub in 0 for h, meaning the limit goes away. So this becomes 1 over square root of x plus 0 plus square root of x, which really is just 1 over 2 square root of x. And they wanted us to tell what our domain of this derivative function would be. Well, we can't have negatives under the radical, or else that would be imaginary. We also can't have 0 there, because it would make the denominator 0. So our domain, then, of this derivative function is that x would have to be greater than 0. And here's a picture of that. Notice in our original, we have positive slopes always. And notice in our derivative graph, we have positive y values always. So that makes sense. So we want to know where the function absolute value of x is differentiable. Well, the only place we could run into problems is when x is equal to 0. So we would say all values of x except 0. And the reason is there is an abrupt change in the slope at that point. Left of there, the slope is always -1. Right of there, the slope is always +1. So if you just think about this graphically, if we were doing our derivative at 0, because remember the derivative has a limit in it, so therefore the left-hand limit would have to equal the right-hand limit. Well, your slope from the left is -1. Your slope from the right is +1. Therefore, it's not going to work out. And we're going to show you this algebraically. X is the absolute value of x. Remember, we've got to think of that as a piecewise function. It is going to be -x when x is less than 0, and it'll be +x when x is greater than 0. We're not going to worry about at 0, because when we do a limit, we're just really concerned about as it's getting close to that. So when we do our limit as x approaches 0, say from the right, we're going to be using this one here. So we'll put in our x plus h minus x over 8. Well, that just becomes the limit as x approaches 0 from the right of h over 8, which is the limit as x approaches 0 from the right of 1, which is just a constant, so that would be 1. And very similar, when we do our limit as x approaches 0 from the left, we're going to be using this function now. So when we sub in an x plus h, the negative will distribute to both, so it'll be -x minus h. And then we'll have minus a -x all over h. So this will be limit as h approaches 0 from the left. We'll be left with, since it's plus a plus, you'll have minus h. So we'll have limit as h approaches 0 from the left of -1, which is just -1. The left-hand limit does not equal the right-hand limit, so therefore not differentiable at 0. Okay, and in general, a function will not be differentiable if there's any corner points or kinks in the graph, which are abrupt changes in the slope. It needs to be a gradual change in the slope for the derivative to exist. A function f is differentiable at a if f prime of a exists. It could be differentiable on the open interval if it is differentiable in every number within that interval. Okay, so both those are kind of obvious, I think. There's another visual of the graph we just did where it's clear that the left-hand slopes of 0 and the right-hand slopes of 0 are creating an abrupt change. In other words, there's no tangent line at x equals 0. If a function is differentiable at some point, we also know it is continuous at that point. Is the converse true, though? If it is continuous at a point, does it have to be differentiable? Well, we just showed an example that proves this false. Absolute value of x is continuous at x equals 0, but it is not differentiable there. So the reverse does not necessarily work. So we'll look at one more example in this video. We're going to find our derivative as a function of x, so f prime of x. And this one's going to be a little bit messier than the other ones. So we'll do our limit as h approaches 0. We'll do f of x plus h, which means anywhere there's an x, we'll sub in an x plus h. So we'll have 1 minus, in parentheses, x plus h over 2 plus x plus h, minus our f of x, which is 1 minus x over 2 plus x, all over h. If we distribute that negative on top, it'll be the limit as h approaches of 1 minus x minus h over 2 plus x plus h minus 1 minus x over 2 plus x, all over h. And we're going to have to get a common denominator now. For that common denominator, we are going to have to multiply that left fraction top and bottom by 2 plus x, and the right fraction top and bottom by 2 plus x plus h. So off to the side first, I'm going to do 1 minus x minus h multiplied by 2 plus x. Okay, and this is going to be our new numerator on the left there. So if we distribute the 1, we'll just get 2 plus x. If we distribute the negative x, we'll get negative 2x minus x squared. If we distribute the minus h, we'll get minus h. Now, there's no like terms there, so we'll just write that out in our numerator. And I'm just going to go ahead and write the common denominator, 2 plus x plus h times 2 plus x. We just multiplied out our new numerator here, so we'll have 2 plus x minus 2x, x squared minus 2h minus xh. We're going to have minus, and then we'll have whatever our new numerator is for that part. So maybe I'll go up here where there's a little more room. So now we'll multiply out 1 minus x times our other denominator, 2 plus x plus h. So when I distribute the 1, I'll just get the same thing back, 2 plus x plus h. When I distribute the negative x, I'll get negative 2x minus x squared minus xh. And we'll bring that down here. And now remember, we were dividing everything by h. Well, just off to the side here, if you divide something by h, that's really h over 1. So that's like multiplying by 1 over h. So really, we're multiplying this current fraction I have written by 1 over h, meaning the h will just end up on the bottom with that stuff. Kind of like if you divide by 2, it's like you multiply by 1/2. So the top gets a 1 and the bottom gets a 2. Okay, just here we have h. So we'll distribute our negative. We'll have the limit as h approaches 0. We'll have 2 plus x minus 2x minus x squared minus 2h minus xh. When we distribute the negative, we'll have minus 2 minus x minus h plus 2x plus x squared plus xh. We are all over h times 2 plus x plus h. We've got a positive 2, we've got a negative 2. We've got a positive x, we've got a negative x. We've got a negative 2x, we've got a positive 2x. We've got a negative x squared, we've got a positive x squared. We've got a negative xh, we've got a positive xh. So that's just going to leave us with the limit as h approaches 0 of negative 2h. We have a minus h in there as well. So actually, we'll do it in 2 steps, but we can combine those because they're like terms. So minus 2h minus h will give us minus 3h, really. You can now divide out the h's. That leaves us with the limit as h approaches 0 of negative 3 over 2 plus x plus h times 2 plus x. Sub in the zeros for the h's. We'll have limit as h approaches 0 of negative 3. Oops, sorry, actually the limit would be gone because we're subbing in the 0. Of negative 3 over 2 plus 0 times 2 plus x. And this would just give us negative 3 over 2 plus x squared. And this is our derivative f prime of x as a function. It can give us the slope of the tangent line for any given x value. That's it for this video. We'll see you next class period.